1 Faraday electricity was passed through Cu2 plus Cu, where the concentration of Cu2 plus is 1.5 molar, and 0.1 Faraday electricity was passed through Ag plus Ag, where the concentration of Ag plus is 0.2 molar electrolytic cells. After these two cells were connected, as shown below, to make an electrochemical cell, what is the EMF of the cell thus formed at 298 K? We have to find out the answer in terms of millivolts. The given values are reduction potential of Cu2 plus to Cu and the reduction potential of Ag plus to Ag, and in the Nernst equation, whatever the term we use, that was given as 0.06 volt. So we have to use Nernst equation to find out the electromotive force. Nernst equation is Ecell equal to Ecell Standard minus 2.303 RT divided by NF log Q base 10. Now Ecell Standard is the standard reduction potential of the cathode minus the standard reduction potential of the anode. This problem has two layers. First, we need to figure out the new concentrations, because concentration of Cu2 plus and concentration of Ag plus is given, but they are initial concentrations. Once the electricity is being passed, the concentration of Cu2 plus as well as the concentration of Ag plus is going to change. So that we need to figure out first before we apply those terms to the Nernst equation. So let us first find out the new concentrations. We have Cu2 plus on one side. Cu2 plus, if it gains 2 electrons, then it can become Cu. So that means to convert it into Cu, we require 2 mole of electrons. We know that 1 mole of electrons, the charge of 1 mole of electrons is equal to 1 Faraday, that is equal to 96,500 coulomb per mole. But do we have 2 Faraday here? No, we have only 1 Faraday electricity. So therefore, how much it would get converted? Only half a mole, isn't it? If we have 2 Faraday electricity, then we can get 1 mole of copper. But we have only 1 Faraday of electricity. So therefore, with that, we can get only half a mole of Cu, isn't it? So therefore, now what the concentration of Cu2 plus would be? The new concentration. Initially, the concentration of Cu2 plus is 1.5 molar before the electricity is passed. So after the electricity is passed, what it would become? So Cu2 plus left is equal to whatever is the initial value, Cu2 plus initial minus Cu2 plus consumed, isn't it? So now how much is consumed here? 0.5 molar is consumed. So 1.5 molar minus 0.5 molar, therefore that is equal to 1 molar. So that's the new concentration of Cu2 plus. Likewise, we have Ag plus. If Ag plus gains 1 electron, then it would become Ag. But for that, 1 Faraday is required. But how much we are passing? Only 0.1 Faraday. That's what is given in the problem, isn't it? So if we are passing only 0.1 Faraday, we will get 0.1 Ag. So therefore, the concentration of Ag plus left is equal to whatever the concentration we have for Ag plus initially minus Ag plus consumed, isn't it? So therefore, this will be equal to, initially we have 0.2 molar minus consumed is 0.1 molar. So therefore, the new concentration is 0.1 molar. This is the value we should use in the Nernst equation. If we use the older values, you cannot get the correct answer. Now, let us come to the actual problem. We figured out that what are the new concentrations of Cu2 plus as well as Ag plus. Now, we need to figure out where the oxidation is happening and where the reduction is happening. The reduction potentials are given. We know that if the reduction potential is higher for a given species, what it means? It means it can easily get reduced. That means it is a strong oxidizing agent. Here 0.34 is definitely less than 0.80. So, a higher and more positive reduction potential indicates that it has a greater tendency for a species to gain electrons and get reduced easily. So, higher standard reduction potential means it has the oxidizing tendency. It is a measure of the oxidizing tendency, isn't it? So, therefore, which one will get reduced here quickly? Ag plus will get reduced quickly because that has the higher value. So, therefore, this is the cathode and this is the anode here. The simple way that you can remember is whichever has the higher reduction potential, that will get reduced quickly. That has the tendency to gain the electron quickly and becomes a neutral species. Okay? So, therefore, in this case reduction is happening at this end because it is always anodic oxidation and cathodic reduction. So, reduction is happening here. Ag plus gaining an electron and becoming Ag, and here oxidation is happening in the anode. So, Cu becoming Cu2 plus and giving 2 electron. So, that means the electron flow is this way, isn't it? So, that part is clear. Now, let us come to the Q part. So, we mentioned that at the anode oxidation is happening. So, therefore, this is Cu giving Cu2 plus 2 electrons, and then at the cathode reduction is happening. Ag plus gains an electron and becomes Ag. To balance the equation, we have to multiply by 2 here. So, this is 2, this is 2 and this is also 2. Therefore, 2 electron we can cancel. Therefore, 2 Ag plus Cu giving Cu2 plus 2 Ag. Therefore, the quotient here is product here Cu2 plus concentration divided by reactant Ag plus square, because we have the stoichiometric coefficient 2 here. We do not write the solids in the reaction quotient equation. So, therefore, Ecell is equal to E standard cathode minus E standard anode minus 1 by N times this 2.03 RT by F is given as 0.06 volt times log concentration of Cu2 plus that we found is 1 molar, isn't it? This is Cu2 plus divided by Ag plus square. So, therefore, the concentration of Cu2 plus, that is the new concentration that we found was 1 molar divided by concentration of Ag plus, that is the new concentration of Ag plus that we found was 0.1. So, this is 1 divided by 0.1 square. 0.1 we can write it as 1 by 10 whole square. So, therefore, this is 1 by 100. So, that we can put it as simply when it comes up it would become 100. I am writing it as 10 square. So, therefore, this will be equal to E standard cathode is 0.80 volt minus E standard anode is 0.34 volt minus N factor is 2 times 0.06 volt times this will be 2 log 10 base 10. So, this 2 we can cancel. So, therefore, this will be 0.46 volt minus 0.06 volt, and that is equal to 0.40 volt. But we need the final answer in terms of millivolts. So therefore this will be 400 millivolt. The EMF of the cell will be 400 millivolt. So therefore 400 is the correct answer here. The resistance of conductivity cell with the cell constant 1.14 per centimeter containing 0.01 molar potassium chloride solution at 298 K is 1500 ohm. The molar conductivity of 0.01 molar KCl solution at the same temperature in Siemens centimeter square per mole is how much? We know that molar conductivity lambda m is equal to specific conductance, that is kappa, divided by molar concentration. We also know that kappa is equal to cell constant divided by resistance. Cell constant value here it is given as 1.14 per centimeter divided by resistance value is given as 1500 ohm. So therefore we can write that 114 times 10 to the power minus 2 divided by 15, and let's send these 10 to the power 2 also up. So in that case 10 to the power minus 2 once again, and then per ohm per centimeter. Therefore let us first figure out 114 divided by 15. So 114 divided by 15, we can do it 7 times. So therefore 105, remaining 9 we can't divide, so put as 0 and raise it to the decimal, and now we can do it 6 times. So therefore this is equal to 7.6 times 10 to the power minus 4 per ohm per centimeter. So therefore molar conductivity is equal to 7.6 times 10 to the power minus 4 Siemens, because per ohm is Siemens. Therefore I am just directly writing it as Siemens per centimeter divided by molar concentration is 1 times 10 to the power minus 3 mole per liter. Now the tricky part in this question is unit conversion. We have to change per liter to per meter cube, and then per meter cube we have to change it to per centimeter cube, so that we can do the unit cancellation in a proper way. That's the tricky part in this question. We know that 1000 liter is equal to 1 meter cube. So therefore 10 to the power 3 liter is equal to 1 meter cube. Now if we make it per liter, then we have to put minus everywhere. So 10 to the power minus 3 per liter is equal to 1 per meter cube. So therefore per liter is equal to per meter cube times 10 to the power plus 3, isn't it? Because we are bringing this to the other side. So therefore when it comes to the numerator it would become positive 3. Therefore molar conductivity is equal to 7.6 times 10 to the power minus 4 Siemens per centimeter divided by 1 times 10 to the power minus 3 times mole times 10 to the power 3 per meter cube. So therefore 10 to the power minus 3, 10 to the power plus 3 we can cancel, and then we have to convert now per meter cube to per centimeter cube. That would be 10 to the power minus 6 per centimeter cube. Why? Because 1 meter is equal to 100 centimeter. So therefore 1 meter is equal to 10 to the power 2 centimeter. So when we make it per meter, it would be equal to 10 to the power minus 2 per centimeter. Now if we cube it on both sides, then we would reach it here. So therefore, this is equal to 7.6 times 10 to the power minus 4 Siemens per centimeter divided by 1 mole times 10 to the power minus 6 per centimeter cube. So therefore, 10 to the power minus 4, 10 to the power minus 6, if we cancel it, we would have 10 to the power minus 2 per centimeter cube. If we cancel it, we would have per centimeter square. So therefore, let's bring everything up. So in that case, what we would have is 760 Siemens centimeter square per mole. So that's the value of molar conductivity. Therefore, the correct answer here is 760. Consider the following reaction. Permanganate ion is getting reduced to manganese 2 plus. The quantity of electricity required in Faraday to reduce 5 moles of permanganate ion is how much? What would be the oxidation state of permanganate ion here? It would be X plus 4 times minus 2, because we have to give minus 2 as the charge for oxygen. So therefore, X is equal to minus 1 plus 8. Therefore, X is equal to plus 7. The oxidation state of manganese is plus 7. So that's why it is written as 5 electrons here. So therefore, to reduce 1 mole of permanganate ion to 1 mole of manganese 2 plus, we require 5 moles of electrons. And we know that charge of 1 mole of electrons is equal to 1 Faraday. So therefore, if we have to reduce 5 moles of permanganate ion, then it would be equal to 5 times 5, 25 Faraday, isn't it? If charge of 1 mole of electrons is equal to 1 Faraday, then to reduce 1 mole of permanganate to 1 mole of manganese 2 plus, we require 5 moles of electrons. So therefore, we have to multiply the entire thing with 5. Therefore, 5 times 5, and that is equal to 25 Faraday. Therefore, 25 is the correct answer here. Given that the standard potentials E naught of copper 2 plus becoming copper and copper plus becoming copper are 0.34 volt and 0.522 volt respectively, the E naught of copper 2 plus becoming copper plus is how much? If copper 2 plus has to become copper, we require 2 moles of electrons, isn't it? So therefore, the N value is equal to 2 here, and for that the E naught value is given as 0.34 volt. If copper plus has to become copper, for that we require only 1 mole of electrons. So therefore, N value is equal to 1 here, and for this one the E naught value is given as 0.522 volt, and we need to figure out the E naught value for copper 2 plus becoming copper plus. For that also we require only 1 mole of electrons, and E naught value we need to figure out. We know that delta G standard is equal to minus NF Ecell standard. So therefore, let us keep this one as delta G1 standard, this one as delta G2 standard, and this one as delta G3 standard. So therefore, delta G3 standard is equal to delta G1 standard minus delta G2 standard. So therefore, minus 1 times F times E3 standard is equal to minus 2 times F times 0.34 volt, and then we have minus here, we also have another minus here. So therefore, it would become plus 1 times Faraday times 0.522 volt. Therefore, minus Fe3 standard is equal to minus 0.68 volt plus 0.522 volt. Let's take the Faraday constant outside. So, we can cancel the Faraday constant because it is common on both sides. So, therefore, minus E3 standard is equal to minus 0.680 plus 0.522. 10 minus 2, 8, 7 minus 2, 5, 6 minus 5, 1. So, therefore, minus 0.158 volt. We have minus on both sides. Therefore, E3 standard is equal to plus 0.158 volt. Therefore, option 2 is correct. The cell potential for the following electrochemical cell is given as 0.801 volt at 298 Kelvin. The reaction quotient for the above reaction is given as 10 to the power minus 2. In that case, what is the number of electrons involved in the given electrochemical cell reaction is? Standard reduction potential values are given. The reason why I am saying they are reduction potentials is because zinc 2 plus has to gain 2 electrons, then only it can become zinc. Likewise, tin X plus, we have to find out the X value here, has to gain X number of electrons so that it can become tin. So, therefore, standard reduction potential values are given, and this is the value we use in the Nernst equation. We know that Nernst equation is Ecell is equal to Ecell standard minus 2.303 RT by NF log Q. Q value is given as 10 to the power minus 2, and we know that Ecell standard is equal to standard reduction potential of the cathode minus standard reduction potential of the anode. Now here, which one is anode, which one is cathode? Obviously, whatever is there on the left hand side of salt bridge, that is anode. Zinc is losing 2 electrons and becoming zinc 2 plus. Whatever be the cell, it is always anodic oxidation and cathodic reduction. Here, tin X plus is gaining X number of electrons and becoming tin. So, that is reduction. So, therefore, Ecell standard is equal to cathode value is 0.008 minus anode value, the reduction potential is given as minus 0.763. So, therefore, this is equal to 0.771 volt. Therefore, 0.801 is equal to 0.771 minus 0.06 divided by n log 10 to the power minus 2. We can bring this 10 to the power minus 2 here. We have another minus sign here. So, therefore, that would become plus. Therefore, 0.801 minus 0.771 is equal to 0.12 divided by n. Therefore, this would be 0.030 and that is equal to 0.12 by n. Therefore, n is equal to 12 times 10 to the power minus 2 divided by 30 times 10 to the power minus 3. We will have 10 to the power minus 1 in the denominator, 1010 we can cancel. So, therefore, n value is equal to 4. Therefore, 4 electrons are involved. Therefore, the correct answer here is 4. Consider the following half cell reaction: dichromate ion gaining 6 moles of electrons and becoming chromium 3 plus, 2 moles of chromium 3 plus. The reaction was conducted with a ratio of concentration of chromium 3 plus whole square, because we have the stoichiometric coefficient 2, divided by dichromate ion, and that is equal to 10 to the power minus 6. Basically, part of the reaction quotient value is given. In that case, what is the pH value at which the EMF of the half cell will become 0? We have to find out the nearest integer. Half cell reduction potential is given, and this is the term that we use in the Nernst equation. Now, the condition given here is EMF of the half cell will become 0. So, that means the E cell value is equal to 0 volt. That is the condition given here. Therefore, we know that as per Nernst equation, E cell is equal to Ecell Standard minus 2.303 times RT by NF log Q. Q is the reaction quotient. So, in this case, the quotient is equal to concentration of chromium 3 plus whole square, and we don't enter liquids or solids in the reaction quotient. So, therefore, we can leave the products as it is, divided by concentration of dichromate ion times concentration of H plus to the whole power 14, because we have 14 as the stoichiometric coefficient. Therefore, let us substitute this in the Nernst equation. Now, before doing that, we also know that Ecell Standard is equal to the standard reduction potential of the cathode minus the standard reduction potential of the anode. One question that may come to many of you is, what is the reduction potential of the anode here? That value is not given. The reaction provided is a half cell reaction and not a full electrochemical cell. However, if you carefully see the standard half cell reduction potential in this case, they have mentioned H plus. What this means is that the potential of this single electrode measured against a standard hydrogen electrode. We know that for standard hydrogen electrode, it is 0 volt because that is a reference electrode. So, that is a tricky part in this question. So, therefore, for the anode, we have to take it as 0. Please do not think that the value is not given. So, therefore, for the cathode, the value given is 1.33 volt. So, therefore, the E cell standard is equal to 1.33 volt. Therefore, 0 is equal to 1.33 minus 0.059 divided by 6, because 6 moles of electrons were involved in the reduction process, times log 10 to the power minus 6. Why 10 to the power minus 6? Because the concentration of chromium 3 plus whole square divided by concentration of dichromate ion is given as 10 to the power minus 6 times we have H plus ion concentration. So, if we bring that up, then that is H plus concentration to the whole power minus 14, because we have 1 by H plus to the power plus 14. So, we brought it up, therefore, it became minus. Now, this is log A times B. Log A times B is log A plus log B. So, let us rearrange this equation. 0.059 divided by 6 times minus 6. We are just bringing this minus 6 to the front. Log 10 base 10 is 1. So, times 1. And then let us bring this minus 14 also to the front. So, therefore, minus 14 times log H plus ion concentration. And we know that pH is equal to negative logarithm of H plus ion concentration. So, therefore, let us substitute that here, and this is equal to 1.33. Therefore, 0.059 divided by 6 times minus 6 plus 14 times pH is equal to 1.33. So, therefore, minus 6 plus 14 times pH is equal to 1.33 times 6 divided by 0.059. 1.33 times 6 would be 6 times 3 18 remaining 1, 6 times 3 again 18 plus 1 19 remaining 1, 6 times 1 6 plus 1 7. So, 7.98 divided by 0.059, and that we can write it as 798 times 10 to the power minus 2 divided by 59 times 10 to the power minus 3. So, we will have 10 to the power minus 1 in the denominator. So, if we send that up, then it would be 7980 divided by 59. This is what we need to figure out now on the right hand side. So let's do the long division. 7980 divided by 59. We can do it one time. So 59 remaining 20. Let's bring down the 8. Now we can do it 3 times. 3 times 59 is 177, remaining 31. Let's bring down this 0 also. So now we can do it 5 times. 5 times 59 is 295, remaining 15. We can't divide, so put a 0 and raise it to the decimal. So now we can do it 2 times. 2 times 59, 118, remaining 32. We can't divide, so put a 0. Now we can once again do it 5 times. So therefore 135.25. So minus 6 plus 14 times pH is equal to 135.25. So therefore pH is equal to, let's bring the minus 6 to the other side. In that case it would be 141.25 divided by 14. So therefore this will be approximately equal to 10. So therefore the correct answer in this case is pH is equal to 10. 10 is the correct answer here. For the given reactions, the electrode potentials are given, tin 2 plus becoming tin and tin 4 plus becoming tin. The magnitude of standard electrode potential for tin 4 plus becoming tin 2 plus is how much? We have to find out the answer in terms of 10 to the power minus 2 volt. So if it becomes negative, then we have to change the sign, but if the value comes positive, we are going to keep it as it is. And we know that delta G standard is equal to minus NF Ecell standard. Based on the equations given, we are going to write two equations. One is delta G1 standard is equal to minus 2 because 2 electrons are involved times Faraday constant times Ecell standard value is given as minus 0.140 volt. So therefore minus 0.140, and that would be equal to 0.280 Faraday. And then delta Z2 standard is equal to minus 4 Faraday because 4 moles of electrons are involved times Ecell standard, that is 0.010. Therefore this is equal to minus 0.040 Faraday. Let's say this is equation 1 and this is equation 2. Let us subtract equation 1 from equation 2. In that case we can write that tin 4 plus 4 electron minus tin 2 plus minus 2 electron. On the right hand side it would be 0, but then this would become 2 electron. So therefore let us send tin 2 plus this side. So therefore tin 4 plus gaining 2 electrons becoming tin 2 plus. So therefore delta G3 standard is equal to delta G2 standard, that is minus 0.040 Faraday, and then again minus because we have a minus sign in the equation, 0.280 Faraday. So therefore minus 2 times Faraday times Ecell standard, because here also it involves 2 moles of electrons, that's why 2 here, is equal to minus 0.32 Faraday. So Faraday constant is common on both sides, therefore we can cancel that. Minus sign is also common on both sides, we can cancel that. So therefore Ecell standard is equal to 0.32 divided by 2, and that would be 0.16, which we can write it as 16 times 10 to the power minus 2 volt. So therefore 16 is the correct answer here. The quantity of electricity in Faraday needed to reduce 1 mole of dichromate ion to chromium 3 plus is how much? We know that charge of 1 mole of electrons is what we call it as 1 Faraday, because charge of a single electron is equal to 1.602 times 10 to the power minus 19 coulomb. So therefore, that value multiplied by Avogadro number is what? The charge of 1 mole of electrons. So therefore, charge of 1 mole of electrons is equal to 1.602 times 10 to the power minus 19 coulomb times Avogadro number, that is 6.022 times 10 to the power 23 per mole. This one will be approximately 96,500 coulomb per mole, and that is what we call it as 1 Faraday. Now here in the dichromate ion, we first need to see the oxidation state of chromium. So therefore, let us keep it as 2x, because we have 2 chromium atoms, plus 7 times minus 2, because valency of oxygen is 2, therefore the charge we give it as minus 2, and that is equal to minus 2 because the net charge is 2 minus. Therefore, 2x minus 14 is equal to minus 2. So therefore, 2x is equal to plus 12. Therefore, x is equal to plus 6. Chromium is in plus 6 oxidation state in the dichromate ion. So it is undergoing reduction and becoming chromium 3 plus. But when we have 1 mole of dichromate ion, how many moles of chromium 3 plus we will get? We will get 2 moles, isn't it? Otherwise the equation is not balanced. So therefore, for 1 mole, how many moles of electrons are required? That means we require 6 moles of electrons, isn't it? Because we have to multiply with the 6 moles of electrons, not 3 moles of electrons. Because if you multiply with the 3 moles of electrons, then we cannot get 2 times chromium 3 plus. At that time we have to write only chromium 3 plus, 1 times chromium 3 plus. So therefore, the correct answer is 6 moles of electrons. Therefore, 6 is the correct answer here. That means 6 Faraday. The cell potential for the given cell at 298 K is given as 0.31 volt. The pH of the acidic solution is found to be 3, whereas the concentration of Cu2 plus is 10 to the power minus x molar. What is the value of x is? Standard reduction potential of copper 2 plus becoming copper is given, and also this is the term that we use in the Nernst equation, that is also given. We know that Nernst equation is Ecell is equal to Ecell Standard minus 2.303 RT by NF log Q, where Q is the reaction quotient. Here, what is the anode and what is the cathode? We have a salt bridge here. So whatever is there on the left hand side of salt bridge, that is the anode, isn't it? And whatever is there on the right hand side of salt bridge, that is the cathode. Anode, oxidation happens. So therefore, H2 gas giving 2H plus and releasing 2 electrons. So this is happening at the anode, anodic oxidation, cathodic reduction. And then at the cathode, reduction happens, copper 2 plus gains 2 electrons, becoming copper solid. Therefore, the net reaction is H2 gas plus Cu2 plus giving 2H plus copper solid. This is the net reaction. Therefore, quotient here is concentration of H plus whole square, because we have the stoichiometric coefficient 2 here, and we don't enter solids in the reaction quotient equation because that is constant, divided by concentration of H2, that we can take it as 1 bar, partial pressure of H2. So therefore, simply multiplying 1 with the concentration of copper 2 plus. So that's our reaction quotient. And we also know that Ecell Standard is equal to the standard value for the cathode minus the standard value for the anode. So here H2 is the reference electrode. So for the reference electrode, we keep it as 0 volt. That is not given, but this is something you are supposed to know it. And the platinum acts as an inert conductive metal substrate that facilitates the redox reaction between H2 and H plus in the standard hydrogen electrode. So therefore this value is 0.0 volt, and for the cathode the value is given as 0.34 volt. So therefore the Ecell standard value is 0.34 volt. So let's plug in this in the Nernst equation, and the Ecell value is given as 0.31 volt. Ecell standard value that we got is 0.34 volt minus 0.06 divided by 2, because there were 2 moles of electrons, isn't it, as per the redox equation, times log concentration of H plus was given as 10 to the power minus 3. Why? Because pH value was given as 3. We know that pH is equal to negative logarithm of H plus ion concentration. So therefore H plus ion concentration must be equal to 10 to the power minus 3, so that we can get the pH value as 3. So therefore 10 to the power minus 3 whole square divided by concentration of copper 2 plus, and this will become 0.03. Now for the concentration of copper 2 plus, let's write the value as 10 to the power minus x, because that is what given in the question paper. So therefore 0.31 is equal to 0.34 minus 0.03 times log 10 to the power minus 6 divided by 10 to the power minus x. So if we bring this one up, it would become positive. So therefore it would be log 10 to the power x minus 6, isn't it? So this x minus 6 we can bring it to the front. Therefore 0.31 is equal to 0.34 minus 0.03 times x minus 6, log 10 base 10 is 1. So therefore 0.03 times x minus 6 is equal to 0.34 minus 0.31. I just brought this term to the other side. So therefore x minus 6 is equal to 0.03 divided by 0.03. So therefore x minus 6 is equal to 1. Therefore x is equal to 7. Therefore 7 is the correct answer here. So therefore the value of x here is 7. That's the correct answer. Here is a conceptually intensive question from electrochemistry. This question is not difficult to solve, but concept clarity is required to solve a question like this. In a cell, the following reactions takes place. The standard electrode potential for the spontaneous reaction in the cell is x times 10 to the power minus 2 volt at 298 K. What is the value of x is? Now, if Fe2 plus becoming Fe3 plus, what does it mean? That means oxidation, isn't it? Increase in oxidation number is oxidation, and decrease in oxidation number is reduction. I minus becoming I2. From negative it is becoming 0. Therefore, that is oxidation, or the other way to remember is losing electrons is oxidations, gaining electrons is reduction, and the reverse one is reduction. Now the question says spontaneous reaction. When a reaction would be spontaneous? Only when the standard Gibbs energy is negative, that is less than 0, then only it can be spontaneous. And we know that delta G standard is equal to minus NF Ecell standard. So this means the Ecell standard value that we are going to calculate here has to be positive. The question already gave a clue to us, isn't it? Because so that the delta G standard would be negative. Only if this value is positive, the Ecell standard value is positive, then only the delta G standard would be negative, so that the reaction would be spontaneous. Now, let us check whether they have given reduction potentials or not. Fe3 plus gaining an electron and becoming Fe2 plus, that is reduction. Therefore, this is a reduction potential. I2 gaining 2 electrons and becoming I minus or 2I minus, that is reduction, isn't it? So, therefore, reduction potentials are given here. If standard reduction potentials are given, then how to identify the species, like which one is the cathode, which one is the anode? The higher positive value should be the cathode. That's where the reduction will happen. So, therefore, this is the cathode and this is the anode, isn't it? Now, we know that Ecell standard is equal to Ecell standard of the cathode minus Ecell standard of the anode. Both are reduction potentials. Sometimes people use this equation also, where Ecell standard is equal to Ecell standard of the anode oxidation plus Ecell standard of the cathode reduction. Now, I prefer to use this equation because using this equation means that you have to change the sign. So, therefore, I don't want to do it. If you are comfortable changing sign and doing correctly, that's up to you. But keep it in mind that it's safe to use the first equation, because in that case we don't have to change the sign. So, therefore, the net reaction that is happening here is Fe3 plus gains an electron becoming Fe2 plus, that is reduction, because whatever be the cell, it is always anodic oxidation and cathodic reduction. And then 2I minus, that is iodide becoming iodine, that is oxidation. Now, to balance the equation, we have to multiply this entire equation by 2. Therefore, the net reaction is 2Fe3 plus 2I minus giving 2Fe2 plus I2. Now, keep it in mind that standard electrode potentials are intensive properties. They are not extensive properties. Standard electrode potentials are intensive properties. That means they depend on the nature of the substance and not the amount. Therefore, just because we multiplied here by 2, it doesn't mean that we have to multiply the standard reduction potential by 2. We shouldn't do that. Therefore, Ecell standard is equal to cathode, that is 0.77, Ecell standard of the cathode minus Ecell standard of the anode, that is 0.54. Therefore, that is equal to 0.23, which we can write it as 23 times 10 to the power minus 2 volt. Therefore, 23 is the correct answer here. Nearest integer is 23. Given the equilibrium constant Kc of the reaction is 10 times 10 to the power 15, calculate the Ecell standard of this reaction at 298 K. The term that we use in the Nernst equation at 298 K is given as 0.059 volt. We know that Nernst equation is Ecell is equal to Ecell standard minus 2.303 RT by NF log Q. Q is the reaction quotient. We also know that At equilibrium, Kc is equal to Q. Also, at equilibrium, delta G is equal to 0. This means E cell is equal to 0, isn't it? Because there is no net electron flow. Therefore, the cell potential is 0. This means Ecell Standard is equal to 2.303 RT by NF log Q. Here, copper is becoming copper 2 plus. That means oxidation. Ag plus is becoming Ag. That means reduction. Therefore, at the anode, because whatever be the cell, it is always anodic oxidation and cathodic reduction. At the anode, copper solid is losing 2 electrons and becoming copper 2 plus. At the cathode, reduction is happening. Ag plus gains an electron and becoming Ag solid. But to balance the equation, we have to multiply this entire equation by 2. So, therefore, the net reaction is copper solid plus 2 Ag plus giving copper 2 plus 2 Ag. Therefore, the quotient here is concentration of copper 2 plus divided by concentration of Ag plus whole square, because we have the stoichiometric coefficient 2 here. We don't write solids in the reaction quotient equation because they are constant. Now, this term is given as 10 to the power 16. Therefore, Ecell Standard is equal to 0.059 divided by 2, because 2 moles of electrons, times log 10 to the power 16. So, therefore, 16 we can bring it here. This means 0.059 divided by 2 times 16, because log 10 base 10 is 1. So, therefore, this is 8 times. This means 0.059 times 8. 59 times 8 would be 8 times 9, 72, remaining 7. 8 times 5, 40. So, 47. So, therefore, this will be 0.472 volts. The Ecell Standard value is. This means option 3 is correct. The closest value that we can see is this one. So, therefore, option 3 is correct. For a cell involving copper and silver electrodes, the cell potential is found to be 0.43 volt at 298 K. What is the magnitude of standard electrode potential for copper 2 plus becoming copper is? We have to find out the answer in terms of 10 to the power minus 2 volt. Standard reduction potential of silver plus becoming silver is given as 0.80 volt, and this is the term we use in the Nernst equation. We know that Ecell Standard is equal to standard reduction potential for the cathode minus standard reduction potential for the anode. So, first we need to find out this term, and then we can figure out the final answer, because here they are asking the standard electrode potential for copper 2 plus becoming copper. So, this is the standard reduction potential they are asking, and the cell potential value is given. Now, at the anode, what will happen? At the anode, oxidation happens. Whatever be the cell, it is always anodic oxidation and cathodic reduction. This is the salt bridge. Therefore, on the left hand side, we have the anode. On the right hand side, we have the cathode. So, this means at the anode, copper is losing 2 electrons and becoming copper 2 plus. whereas at the cathode reduction is going to happen. So, this means Ag plus is gaining an electron and becoming Ag solid, but we have 2 electrons involved at the anode. So, therefore, we have to multiply this equation by 2 so that we can balance the equation. So, this means the net reaction is copper solid plus 2 Ag plus is giving copper 2 plus 2 Ag solid. So, that is the net reaction. So, this means the reaction quotient is concentration of copper 2 plus divided by concentration of Ag plus whole square, because we have the stoichiometric coefficient 2 here. Now, let us use the Nernst equation. Nernst equation is Ecell is equal to Ecell Standard minus 2.303 RT divided by NF log Q. So, here Ecell value is given, that is 0.43 volt. Ecell Standard we need to figure out, minus this term is given as 0.06. So, therefore, 0.06 volt divided by number of electrons involved is 2, and then log Q, that is concentration of Cu2 plus, that is 0.001 molar divided by 0.01 molar whole square, isn't it? So, this one we can write it as 1 times 10 to the power minus 3, this one we can write it as 1 times 10 to the power minus 2, but we have square term here. So, therefore, this becomes 10 to the power minus 4. So, this means eventually it becomes log 10 base 10, log 10 base 10 is 1. So, this means Ecell Standard is equal to 0.43 volt plus 0.03 volt, and that is equal to 0.46 volt. This is the Ecell Standard value. So, this means we know that Ecell Standard is equal to standard reduction potential at the cathode minus standard reduction potential at the anode. So, therefore, this is equal to Ag plus becoming Ag minus Cu2 plus becoming Cu, and Ecell Standard is 0.46 volt, and this value is given as 0.80 volt. So, therefore, 0.46 volt is equal to 0.80 volt minus this one. So, therefore, copper 2 plus becoming copper, the standard reduction potential is equal to 0.80 minus 0.46, and that is equal to 0.34, but we need the answer in terms of 10 to the power minus 2. So, therefore, 34 times 10 to the power minus 2 volt. So, this means 34 is the correct answer. So, therefore, 34 times 10 to the power minus 2 volts. For the cell, the correct Nernst equation is which one? Nernst equation is the one that relates cell potential with the concentration of the species involved in an electrochemical reaction. Now, we know that Ecell is equal to Ecell Standard minus RT by NF ln and then the reaction quotient. So, let us say if you have a reaction this way, x times A plus y times B giving, let us say, m times C plus n times D, then you can write the reaction quotient this way: concentration of C to the power of m times concentration of D to the power of n divided by concentration of A to the power x times concentration of B to the power y. Now, for a cell, this double vertical bar, what it means is that it means salt bridge. So, it is always salt bridge in the middle, and then on the left hand side it is the anode, half cell, and then on the right hand side it is the cathode half cell. The single bar represents phase boundary. This is phase boundary, which means that this silver here is solid. Likewise here too, the magnesium here is solid. It is not given, but the phase boundary basically tells us that it is not in aqueous medium, it is solid. We know that whatever be the cell, it is always anodic oxidation and cathodic reduction. Therefore, the half cell reaction that is happening at the anode is magnesium losing 2 electrons and giving Mg 2 plus. And the half cell reaction happening at the cathode is Ag plus gaining an electron and becoming Ag solid. Now 2 electrons are involved on the anode side. That means we need to multiply this entire half cell reaction with 2. So now we can balance this and write the balanced equation. So therefore the net is Mg solid plus 2Ag plus giving Mg2 plus, that is in the aqueous medium, this is also aqueous medium, plus 2Ag solid. And we don't write the solid in the reaction quotient. So therefore the reaction quotient here is Mg2 plus divided by Ag plus square with a negative sign. Do we see anything like that in the option? No. In 1 we don't see it. In 2 we see it, but the reaction is reversed. So therefore that should be the correct option. Because in 3 it is Mg2 plus written, but then Ag plus is not squared. Therefore that is wrong. And in 4 it is written in the reverse way. Therefore this is also wrong. So the only correct option is option 2. In the above diagram, the standard electrode potentials are given in volts over the arrow. What is the value of Ecell Standard for FeO4 2- becoming Fe2 plus? First of all, we need to figure out the oxidation state of Fe in the ferrite ion. We don't know that, therefore let us keep it as X. X plus 4 times. We put -2 for oxygen typically. Therefore 4 times -2, that is equal to -2 because the net charge given here is 2-. Therefore x minus 8 equal to -2. Therefore x is equal to +6. Therefore the oxidation state of Fe in FeO4 2- is +6. This means this is undergoing reduction, isn't it? This process requires how many moles of electrons? We require 4 moles of electrons. So here it is +6. If +6 is becoming +3, that requires how many moles of electrons? That requires 3 moles of electrons. If Fe3 plus becoming Fe2 plus, that requires how many moles of electrons? That requires 1 mole of electron. If Fe2 plus is becoming Fe, then that requires 2 moles of electrons, because everywhere it is reduction, isn't it? If +6 has to become +3, then it has to gain 3 electrons, isn't it? If FeO4 2- gains 3 electrons, then only it can become Fe3 plus. But the question here is, when FeO4 2- becomes Fe2 plus, what is the Ecell standard value? We can calculate that. We know that delta G standard is equal to minus NF Ecell standard, where N is the number of moles of electrons, F is the Faraday constant, and Ecell standard is the reduction potential. So therefore we can write it this way: minus N4F E4 cell that we need to calculate is equal to minus N1F E1 cell minus N2F E2 cell. By the way, we don't need to involve delta G3 standard here, because the question is asking +6 to +2 oxidation state, what is the Ecell value? Therefore we don't need to involve this process. Therefore N4 value is 4, because it requires 4 moles of electrons, times F times E4 standard is equal to minus 3 times F times E1 standard value is given as 2 volts. Therefore, times 2 minus N2 value is 1 times F. E2 standard value is given as 0.8 volts. Therefore, times 0.8. Therefore, minus 4 E4 standard is equal to, F is constant everywhere, therefore, we can remove that. This is equal to minus 6 because 3 times 2 minus 0.8. Therefore, E4 standard is equal to, because minus is common on both sides, this is minus 6.8 minus E4 standard. Minus is common on both sides, therefore, I am removing the minus. So, E4 standard is equal to 6.8 divided by 4. So, therefore, that is equal to, this is 1 times and then 2 remaining 28. 7 times 4 is 28. Therefore, 1.7. Therefore, E4 standard is equal to 1.7 volt. So, this means option 1 is correct. The standard electrode potentials for a few half cells are mentioned below. Which one of the following cells gives the most negative value for delta G naught? We know that delta G naught is equal to minus NF Ecell standard, where N is the number of moles of electrons and F is the Faraday constant, which is 96,500 coulomb per mole, and E standard of the cell is equal to E standard of the cathode, that is the reduction potential, minus E standard of the anode, that is also reduction potential. Now, some instructors do write it this way, that is E naught standard of the anode oxidation plus E naught standard of the cathode reduction. Both are okay, but when you use this formula, you need to constantly change the sign, because normally the reduction potentials will be given in the question paper. Now, let us just verify whether they are reduction potentials or not. Cu2 plus is becoming Cu. When Cu2 plus will become Cu? If it gains 2 electrons, then it can become Cu. That means reduction. Likewise, if you see whatever the values given here, they are all reduction potentials, isn't it? So, when we use oxidation potentials, we have to change the sign of the reduction potential, which I don't want to do it. Therefore, I prefer to use this formula. If you are using this formula, make sure that you are changing the sign appropriately. Otherwise, you will get the wrong answer. Now, when delta G will be negative? Delta G will be negative if E naught of the cell is positive, isn't it? That's the only way delta G can be negative. Basically, the delta G negative is going to be decided by this single value, because N is constant here. How N is constant? The number of moles of electrons is going to be 2 moles everywhere. Now, you might be thinking that here we have only like 1 mole, here we are having 2 mole. But the thing is, if you write the net reaction, so for example, for this cell, if we are writing the net reaction, at the anode oxidation happens. No matter what the cell, it is always anodic oxidation and cathodic reduction. So, zinc losing 2 electrons and becoming zinc 2 plus. At the cathode, reduction happens. So, therefore, Ag plus gaining an electron and becoming Ag. But to balance the reaction, we have to multiply this entire equation with 2, isn't it? Otherwise, we can't balance the equation. So, therefore, everywhere the number of moles of electrons is going to be 2. So, therefore, that is also constant. So, the net reaction in this case is zinc plus 2Ag plus giving zinc 2 plus 2 Ag. That's the net reaction. So therefore, N is constant everywhere, F is constant. So we just have to determine Ecell standard. If that has a more positive value, then that is our correct answer. So let's determine the values one by one. And before doing that, let's talk briefly about the cell notation. There is a phase change here. So this is the phase boundary. So basically it means that these are all solids and these are all in the aqueous medium. And this double vertical bars indicate that there is a salt bridge here to maintain the neutrality of the solution. That completes the circuit. So once again, these are all in the aqueous medium and these are all in the solid phase. So now E naught of the cell in the first case is equal to cathode minus anode, both reduction potentials. That's the way we are going to calculate. So this is all cathode, this is all anode. E naught of the cell is E naught of the cathode reduction potential, that is Ag plus becoming Ag, so 0.80 volt, minus reduction potential at the anode, so that is minus 0.76 volt. So therefore together it is 1.56 volt, because negative will become positive. And then number 2, Ecell standard in this case is reduction potential of the cathode, that is Mg2 plus becoming Mg, so minus 2.37 volt, minus reduction potential of the anode, that is minus 0.76 volt. So therefore this will be equal to minus 1.61 volt. So therefore this is definitely not the correct answer, because in the delta G equation there is another negative sign. So with this negative sign it will become positive. So it is non-spontaneous. And then number 3, Ecell standard is equal to cathode minus anode. So once again minus 2.37 volt minus and then 0.80 volt. Therefore this will be equal to minus 3.17 volt. And then for number 4, it would be Ecell standard equal to cathode minus anode. So cathode 0.80 volt minus anode 0.34 volt. So therefore this will be positive 0.46 volt. So here we have positive 1.56 volt, and then we will be multiplying with the 2 and then the Faraday constant. So therefore this will be most negative. Therefore option 1 is the correct choice here.